Okay, so last time we stopped at measuring multiple moments of correlation function at small scale, and I hope all of you have tried and got something like this, where the top plot is monopole and bottom plot is quadrupole. If you have any trouble, then you can ask me during the first exercise when I will give today, because we are going to do that again today. So far we have gone through idea of measuring correlation function and what are the things involved, what are the kind of question you might want to address. And the main takeaway is like you have to understand, okay, if you look at, there are many publicly available code. If you look at any code, they will start talking about these things. They will start asking you about, okay, what is the range of things you want to look at, what kind of clustering statistics. So if you understand that, you should be able to use anything essentially. And the internal working of the code, you have to like kind of go over it if you want to really, if you're really interested in how things work. And I also hope like people who had no exposure to Python now, they can at least do some simple plots through these sessions. And if you have trouble with that, then please ask. So today we are going to start like estimation of error, right? So in physics, whenever you do any measurement, you have to come up with a error estimate so that you know how precise your measurement is. So the same thing you have to also think about for correlation function studies, and there are several methods to estimate error. Some of them are like very analytical in nature, which is to do with integrating over 4-point and higher order statistics, because you'll be looking at error on 2-point. But there are also methods which are based on simulations, approximate as well as in-body simulation. What I'm going to talk about is jackknife error estimates, which is simple estimates which you can use data or simulation, whatever you're using to measure clustering, you can use it to make error estimates on that. There are limitations of each method, and each has its own regime. Most of the time when you're working at small scale clustering, jackknife is something you can always go ahead and trust with. But when you're working with like more like BO analysis or redshift space distortion, then these method eventually fails. And so you cannot use jackknife. So for all the boss data analysis you see, they don't use methods like this. But anything you're doing with, let's say, Halo model, which is dominated by small scale signal, you can use jackknife error estimates. So what is the idea to start with? So anytime, if you want to estimate error on any measurement, what you need to do is make several realization of your measurement, right? Let's say if you do a measurement 100 times, you can look at its variance, and that will give you an estimate on error. But that is something we cannot do in real universe, because we have only one universe. We cannot do observe it only once. So how do you generate this realization? And that's really where this idea of jackknife comes from. You have just one survey or one simulation, and you want to generate several realization of that. So what you can try to do is you can use a subpart of your simulation or survey and measure your clustering signal, and then see if you do it for several subparts, then how does the variance looks like. But you also need to make sure that your variance is estimate of your full survey and not for the subpart, right? So the way jackknife works is, let's say, so this is like I'm thinking in terms of like, let's say a simulation box where my line of sight is along z-axis, right? So in a 3D box, I will have 3 axes, x, y, and z. So z is my line of sight, which is going inside the box. Now I'll take x and y axis, and I can divide my box in several parts. So which is what I have done here. This is 25 parts I've divided. Now I can take one part at a time and remove that. So I will move all the galaxies in this region. I can remove that and measure my clustering signal exactly the way you have done for the full box. You'll get one realization of your clustering signal. Then you can go ahead and remove the second part, and then you can do it for all of that. So if you have 25 regions like this, which we call jackknife region, you'll get 25 measurement of clustering. Now, when you look at the variance of that statistics, variance of all those realization, that will give you some idea of variance of your clustering measurement, but that won't be variance for the full survey, because every time you're removing only one small region rather than replacing the full region by a completely independent observable, right? And so under certain condition, which is if these regions are independent, then what is shown is if you just scale your variance from a realizations like that by number of regions you have, then that will give you your jackknife variance. So there's an equation here. Right, so this is the equation for variance. So if you just ignore this njn minus 1, where njn is number of jackknife realization, which is 25 for this example. If you just remove this, this is essentially standard expression for variance. If you have many realization of anything, this is how variance is written. But when you'll do a statistic like that, where you only remove a small part, then you just have to scale your variance by number of jackknife realization minus 1. So your standard error is going to go as the square root of that quantity, right? This is variance. So the proof and mathematics behind it is not very complicated, but I won't go over it at this point. If you're really interested, you should just go over and look it up or ask me later. But this is how we are going to estimate the error on our clustering measurement. So all you need to do is take your exact same code and then measure clustering each time, removing one part at a time. And then you can generate any number of these regions, but what decides how many number of regions you could generate? So one of the things you have to worry about, okay, there is a scale at which this region belongs to, right? So let's say if my box is 1 megaparsec in side, I have divided in 5, then it's 0.25. So the scales at which you are looking in clustering signal, that scale should be independent for these things, which means I should not look at scale close to my jackknife region. I should look at much smaller scale than that. So this is how you decide. Depending on how far you want to go, what scales you want to look at, you decide how many regions you want to make, because each region should be bigger than the scales you are looking at when you're estimating errors. That is one thing, but then it's also limited by what is the full volume you have. And this is the main reason, one of the main reason why we don't do it for like very large scale analysis. We don't use jackknife. Otherwise, you can't really generate many such realization with that. So what we are going to do now, so it's the same function which we have been using. So remember to execute first and second code cell, right? The top cell and this cell before doing anything. Otherwise, things won't work. So in this function, there is a number which is called njn, right? Which is 0 by default set to 0. So if you just set njn equals to some number, but that number should be square of any integer, right? So it should be 25 or 16 or 36. That's because we have like two sides and we are dividing in equal parts. So as long as you give njn, which is a square of two numbers, let's say 25, what this function is going to do is going to create such regions and each time remove one part of it and then create several realization. And it will return you the same statistics what it has been giving you. So you should do it for multiple movements, which means everything else stays the same as you did last time. You just have to give an njn. And yeah, so what does it return? Let me just talk about this. So if you are making a call, a function like this, which you're doing something, and you have a new variable now, njn, let's say 25, right? So it how do you get monopole and quadrupole from this function? That was through these two variables from a dictionary. Now you understand what is dictionary. Z0, and then similarly for Z2. So what was Z2? Z0? Z0 was a matrix with two columns. The first column was R, separation. Second column was value of your multiple, monopole. For this case, when it is Z2, then that was Z2. So now when you'll set njn equals to some number, then the output will be something slightly different. Now what the output will look like, so the first column is still R, second column will still be mean Z0, the third column it will estimate error on Z0. So throw that jackknife and the expression I just showed. The fourth column, like as if you didn't do any of this division, like what you originally measured, so it will take the whole box and measure the clustering. And from the fifth column, these are jackknife realization, right? So this is like when you remove your first region, what is your clustering signal? Then when you remove second region, what is your characteristic signal? It will go to 25 in this case, because your engine is 25. So what it really does is essentially calculate these things and then look at the variance of these, which is what your sigma is, scaled by engine minus 1. So this is how your output look like. So now you want to take this output and make a plot with error bar, right? So you want to plot R on the x-axis, monopole on the y-axis, and then error on R, right? And how do you do that in Python? If you haven't used this before, there's a function called pl.errorbar. So the inputs here is whatever you want to plot on x-axis, whatever you want to plot on y-axis, and then you use this argument and give whatever is the y error, sigma y. So this will make a plot of xy with error bar. So I just want you to try it and see how does it look like. And then once you have tried it, we'll go ahead and do the covariance matrix. So this is just the diagonal error estimate. So you have to measure the monopole and quadrupole and make a plot of error bar with jackknife covariance. And I'll have 10 minutes for that. Okay, so did anyone manage to finish and got the error bar on monopole and quadrupole? Something like this. So that's monopole and that's quadrupole with the error bars. I'll wait for 5 more minutes. Okay, so can I have a raise of hand? How many people did it? 1, 2, 3. So everyone having trouble with some sort of error, or you're not understanding how to make a plot? So maybe I think a lot of people have issue with array slicing, which I introduced in the first tutorial. If you have any Python array, let's say, for example, this array, right, which is something like this, it is a 2D matrix. Now you can slice it in any way you want, and the syntax for this is something like, you say my z, z0. So this is a 2D array. Now I can give a square bracket. Anything I write here will be row number. Anything I write here will be column number. So if I want to extract one element, I will write, for example, 0, 0. That will be this element. If I want to extract this element, this will be 1, 1, right? But let's say if I want to extract this row or this column entirely, then the first is correspond to row, and whenever I write column, it means all of it, right? So the first thing is corresponding to row. If I write column, which means take all the rows, and then whatever column you want to extract, just give an index. So this means you'll extract first column. When you say 1, this will extract second column, which is monopole. To get the error bar, you extract third column, which is number 2, right? So this is how you want to do the plot. When you're plotting it, your x here will be right. So this will be your x. For y, you want to change that to 1, and for y error, you want to change that to 2. Is it clear? Yes? Sorry? So in the plot, do you notice the x-axis is in log? So if you look at the x label, it's 10 to the 1 rather than 10. So that is a log axis. So this is another reason why I want you to make this plot, because often you see this in paper and everywhere, but the plots have their own details. So actually to get this shape, you have to make a log-log plot. If you just make linear plot, you'll get very different shape, which is the clustering is very rapidly falling off, right? So this is a log-log relation. And to make this plot, you have to multiply y-axis by r square to see that kind of shape, which is what often is plotted. So you have to multiply r square, your y-axis, and then make that plot. And at the same time, when you're making this plot, you want to plot the error bar. Since you multiplied y-axis by r square, you also need to multiply your error bar by r square to get the right error. Okay, so we'll move a little bit ahead. Given the interest of time, I have two more things I want to go over. One is covariance metrics, and other is actually doing it for data. So for covariance metrics, I will just show you how these things are done. Now, what you have done is you have calculated error on each measurement. So each point of monopole or quadrupole, you have diagonal error. Now, there's idea of covariance metrics, which you have heard many times during your lecture, right? So you know where covariance matrix is used and why I'm talking about covariance matrix? Why is it needed? Anyone? To see the correlation in error. So to define the likelihood, unbiased likelihood, you need a covariance matrix. So you probably have seen this expression where likelihood is some sort of data minus model, which is an array, transpose, C inverse, data minus model. I guess most of you have seen this expression. So what is the C inverse? The C inverse is your inverse of covariance matrix. Let's say if all point you're measuring is independent of each other. If all of the points are independent, then there is not going to be any correlation between those points. So the covariance matrix is going to be diagonal. So if covariance matrix is diagonal, how covariance matrix looks like? So covariance matrix, this element is going to be sigma I is square. So sigma 1 is square, sigma 2 is square, sigma 3 is square, so on. This is sigma 1, sigma 2, sigma 2, sigma 1, sigma 3, sigma 1. So these are standard error on your individual measurement, and if they are correlated, then you'll have these cross terms. So in the case of they are independent, all these cross terms is going to be 0. So you'll only have diagonal error. So the inverse of covariance matrix can be just replaced by, this can be replaced by nothing but 1 over sigma I square. So you have seen this form of expression definitely, which is what is generally introduced to start with, but if data points are correlated, then you have to use full covariance matrix. So it is essential to measure this covariance matrix. Without it, you cannot really do anything with this measurement. So any model you have, we talked about resistive distortion or modified gravity. Your model will have some parameter theta, which will predict your model. You compare with that data, and then you get the likelihood like this. Once you have this, you can sample it and make this posterior plot like the kind of things you have seen. For example, omega matter have some sort of likelihood in Planck paper. This is how you get these things, and you run through MCMC. So covariance matrix for any measurement is very essential, and without that you cannot do anything, which is why I'm going over covariance matrix. Even if you can measure this, if you don't have covariance matrix, you can't do anything. So we actually already have measured everything we need to do covariance matrix. All you need to do is you need to generate several realization, and we did it using jackknife, right? But all you looked at is diagonal error, which means you look at the variance for any particular element. But now what we want to do is we want to look at the variance between different elements. So I look at monopole at one scale and monopole at another scale and how they are covariant. So that is defined here, right? So this is variance, it's just a square of your diagonal element. Now this is covariance, Cij, which can have non-diagonal element, and you take your realizations. So this matrix, you take your realization and you try to see how my first point is correlated with my second point. So this is what Cij will mean. And the expression is pretty standard. It's essentially variance. And then there's another structure which is called correlation matrix. It's mostly useful for the purpose of visualizing things. So the way you do correlation matrix is you take covariance matrix and divide it by diagonal error. So you divide each of this is by sigma 1 square. You divide this one by sigma 1, sigma 2 to the square root. Right? So you divide all of that, and then all your diagonal term will be 1. So that will just tell you what is the correlation structure which will be forced to have value between -1 and 1. Right? So what I wanted you to try to do is actually take your jackknife realization which you have just generated and measure this covariance matrix, which is nothing but this expression. And in Python, there is a function called np.cov. So you just put this and give all of your realization there. That will automatically measure the covariance matrix, but it will measure standard covariance matrix. To get the jackknife covariance matrix, you have to scale it by a factor of nj -1. It's essentially the same factor what was there, right? So you can just try it out. And if you notice, I have this 4 here. You know what does this structure means? What I'm really asking here? Right. So I'm just asking it to not take first 4 column, because first 4 column are what? Those are R, mean, error, and variance. So those are not the realization. My realization starts from the 4th column. So this is again matrix slicing, which I just talked about. I'm saying take all the rows, but take only columns from the fourth column. So I'm ignoring the first 4 column because those are not my realization. And this will construct your covariance matrix. So the covariance matrix plot looks something like this. Given the interest of time, I will not ask you to do it now, but this is how it looks like. The top plot is covariance matrix for the monopole, and the bottom is correlation matrix. So you can see covariance, you can't see anything because error in different diagonal elements are very different, so it's very hard to see in the color bar, which is why I've also plotted correlation matrix, which is 1 across the diagonal, and there is some cross diagonal term. It's hard to see in the projector, but there's a lot of structure and there's a lot of noise there. So this is the covariance matrix for the monopole. You can also do this for the quadrupole. I've done exactly the same thing. I've just extracted the quadrupole moment and then measure the covariance matrix and correlation matrix for the quadrupole. But in actual analysis, you also need to worry about what is the correlation between monopole and quadrupole. So there's going to be cross term, right? So the monopole values are also correlated with quadrupole and not just monopole, different scales of monopole. So you actually have to construct a combined big covariance matrix, which will be much bigger than this, which will look something like this. This is the covariance matrix. You'll often see these plots when you look at large scale structure analysis. They will always show you a plot of correlation matrix. So what this is the correlation between monopole. So different scale of monopole. This is the correlation of different scale of quadrupole. This is the correlation between monopole and quadrupole. And this is always going to be a symmetric matrix, right? By definition, this is a symmetric matrix. So you also need to account for the term here. And you see the matrix looks very noisy here. Any guess why it is so noisy? The whole matrix looks very noisy. It doesn't look like there's a very concrete structure here. What we are looking at, we should be looking at some concrete structure because this is coming from the gravitational evolution of the field. So the reason this is noisy is because I just have 25 realization. And I'm creating a covariance matrix which is actually quite big size. So there's a lot of noise there because I have very few realization. If I want to measure non-noisy covariance matrix, I need many more realization. So I'm limited by my data volume. And if you'll actually look at covariance matrix which is not noisy, you'll see very clean structure, much cleaner structure than what you see here. And there are a lot of issues when you try to invert a noisy covariance matrix. So this all comes from the statistical and linear algebra analysis. So whenever you're trying to invert a noisy covariance matrix, you should be a little bit scared to start with. So I will not ask you to actually try to do this in the interest of time, but because I quickly want to go to the data. So there, I've generated two data files. These are SDSS data. And what these data contains is, it's a spectroscopic sample. Do you understand what it means by spectroscopic survey? Anyone? What's the meaning of a spectroscopic survey? How is it different from a photometric survey? So let's say I want to go out and observe the sky. What I'm going to do, I'm going to put my telescope and take images. That's the first way to observe the sky. You'll have a CCD. So all you have is images. In your image, you can look at galaxies and you can find where those galaxies are. So what you will get? You'll get for each galaxy right ascension and declination. Right? So that's a point in your sphere. But you don't know how far these galaxies are. It's very difficult to gauge the distances, especially if galaxies are far away. They're not really going to move. So to get the galaxy distance, you have to measure something called redshift. Right? All of you heard about redshift. Now this is end of cosmology school. So you have to measure redshift. The way you measure redshift is you take your images, figure out where these galaxies are, and then go and measure spectra for each of these galaxies. So you'll measure spectrum, which is lambda versus some flux, and then you'll see some feature. So you have seen several, for example, you have seen the Lyman alpha forest, Tirth was showing today, and then you'll have Lyman alpha line. So you'll see many features in your spectra, and you want to figure out from the spectra where the lines are shifted. That will give you redshift. So you measure spectra. This is what, whenever I say spectroscopic survey, I mean it's a survey where we are measuring spectra of galaxy and not just images. And whenever I say photometric survey, I'm just measuring images of galaxies. So I'll just have how bright our galaxies are and what is the RA deck of that galaxy. In a spectroscopic survey, you also have redshift. So now you have RA deck and redshift. So you have three coordinate. We are living in three-dimensional universe, unless you work in string theory. So now you can precisely figure out where these galaxies are located, except the fact that you don't have distance, you have redshift. So you have to convert redshift to distance, which you all have seen in several lectures, how the redshift distance relation looks like. So you assume a cosmology, and then you convert redshift to distance. Now you will have three-dimensional location. So you can now convert in any coordinate system. Let's say Cartesian, you go to XYZ, or you work with polar. What this gives you, in some part of the universe, for each galaxy, you know its location in 3 dimensions. That's very important. You know the location, it's in 3 dimensions. So now you can measure 2-point clustering. Now you can do this pair count. You can go to the survey and look at, okay, as a function of distance, how many galaxies do I find? That's exactly what we have been doing all this long, right? But it's just that in data, you'll have RA-deck redshift to start with, and then you have to convert that to get that 3-dimensional distance. So this is what you're going to have in data, RA-deck redshift, and this is what is there in those files which I've extracted. So any public survey, public data of this kind of survey will provide files which are not exactly in this form, which are in something called FITS file, but I've just extracted these 3 quantity. So I want you to just try and explore this file very quickly. So if you load the file, there will be 3 columns, RA-deck and redshift. So I just want you to load the file and make a plot of RA-deck redshift and just visualize in your head and see where these galaxies are living in. You already know how to splice an array. So when you load, it will be array with 3 columns. If you want to plot any column, I just told you how to do that, which is column on the first axis and whatever index you want. Is it clear what I want you to do? So I want you to load this data file, which contains galaxies from SDSS, and then just make a plot of its RA-deck and redshift and just try to understand where these galaxies are living in. Just visualize it. So try to do it quickly. I'll have 5 minutes for that. Anyone got something like this? So this is RA and DEC plotted from the data file. So, okay, yeah, so some people have got it. So just what I'm trying to say is there's a certain part in the sky which we have observed. This part is mostly contiguous, but there are these regions where we don't have any galaxies, right? There are all these holes which you need to understand. So that's something that has to do with something called survey mask. So what is difference in this data set compared to what you have been using, which is a simulation in a box? What is the main difference which you need to worry about when you want to measure clustering statistics for this? Right, so exactly what Shabir said. There are missing parts in here, right? So when I will do, so let's go back to the definition. What is correlation function? It's the excess probability of finding a pair of galaxy separated by certain distance compared to random distribution. So to any time you want to measure the correlation function, you have to compare it with a random distribution. Now the fact that I don't have any galaxies, if this was because there's no galaxy there, then that is fine, but that's not the reason. The reason I don't have any galaxies here because they are masked, they are different things, they are bright stars, or some other reason we could not get data in that part. So now you need to remove these regions from your random distribution as well. So when you generate a uniform random distribution, you need to remove this part of the sky, which is why all of these survey always come with and talk about a random catalog, which is also something you have. So this is the file. This is a random catalog. This again has array, deck, and redshift, which is 3 column. But now this random catalog contains the survey mask. So if you'll make a plot of this random catalog in array, deck, you'll get exactly the same feature. You should see exactly the same feature. Also, if you'll plot redshift distribution of these things, you'll see exactly the same distribution. That's by construction. So, yes. Yes. So you want to create a uniform random in the volume, and you remove the points from the mask region, and you want to have same redshift distribution because there are reasons why redshift distribution is not uniform. Okay. Yeah, I'm not going to take too long from now. Now that you understand the data. So far when I was asking you to calculate clustering for simulation, I mentioned random catalog, but we never had a file for it. But we do need a file for this in terms of data because of these issues, right? So now you have a data file and random file. And what I want to do is like quickly, essentially repeat the exercise which you did with simulation, but with data. But there will be certain changes. First of all, now you have to also provide a random file, right? So you are already providing data file. Now you also have to provide a random file. You know the file name already is given there. But yes. So how to provide random file? You just say, okay, rand file equals to whatever the file name. Right now it's empty. So you add that there. And then everything else like SAMP mode, all the binning and everything will stay the same. You can still work with that. And I want you to make that contour plot which you made for the correlation function. But there are a few more things. Let me just quickly go over. For example, a few more things which I never mentioned earlier, just to avoid complication. PBC equals to 1. What does that mean? That means periodic boundary condition. So I'm sure all of you are familiar with periodic boundary condition. If you have a cubic box, you want to have periodic boundary condition, you say, okay, right side of the end is same as left side of the end. So when I was measuring these things for simulation, I was always applying PBC equals to 1, which you cannot do anymore. So you should set PBC equals to 0 when you're doing it for data. Another thing I was always using is LOS equals to 1. So LOS is line of sight. So we always said Z-axis in the box is my line of sight. That's no more the case for real survey because now you're looking at the sky. So the line of sight is defined by midpoint between the pair of galaxies. So you have to say line of sight equals to 0. That's how the code knows, okay, now you're dealing with data. And the last thing is this file type. So earlier we were providing X, Y, Z coordinates. Now we are providing array, deck, and redshift. So you need to tell the code, okay, these are array, deck, and redshift and not X, Y, Z. So you need to internally convert this in X, Y, Z. So to do that, you just say, in place of txt, you just say polar txt. Polar means it's polar coordinate. The file you're providing is polar coordinate. So you just say polar txt. With those changes, if you run it and you make the plot, you should essentially see very similar feature what you had seen earlier. So something like this. This is for simulation. But sorry, range of R. So that is something you have to decide, depend on what feature you want to look at. The only constraint is don't go for R more than 30, otherwise it will take too long to compute. Yeah, so this is actually, I've done the same thing for data. So I'll just give you 5 minutes to give it a try. And if you can do that, now you know how to do this for data as well as simulations. And you also know how to do covariance metrics. Yeah, so you can't do RSD equals to 1 now because now you don't have velocities. These are real data. We did that with simulation. So okay, there are 3-4 people. If you're getting error, then first thing you should do is really look at carefully all the inputs you're providing. So most of the time I've seen people are mixing different things, like what sampling you're giving versus what range you're giving. So if you're getting error, the first thing is just try to see what inputs you're providing very carefully. Okay. Apart from that, you should get this plot pretty easily. I think I'll just stop at this point. If you have any difficulties, if you're getting error, feel free to contact me. I'm here rest of the week. And if you have any questions, you can also write me email or discuss over Slack.